Hello, everyone. How are we doing today? We're chatty today, I guess. All right. So, today we are going to talk about general changes of variables. Okay. And I've already previewed this idea quite a bit to set us up for this. So, this will be a short section, and then we'll transition into talking about review material for our exam at the end of the week, covering chapter 15. Okay. So, the thing that the book starts off mentioning is something that I have mentioned to you all before, which is if we have some single dimensional integral here, and what we want to do is go through the process that we normally refer to as U substitution. Okay. What we're going to do is we're going to replace the variable x with some function. Now, the way that we're going to do this is we're going to do it kind of backwards. Is x is going to be replaced by some parameterizing function here. Okay. And when we do that, if we take the derivative of this expression with respect to u now, we end up with this. Okay. And under this transformation now, we have new limits of integration from our transformation. I didn't write that down, but that's not the most important detail here. Okay. X gets replaced with gu, and dx gets replaced with g prime of u du after we rearrange this expression. Okay. I have no idea what was causing that high-pitched whine, and I apologize for however that came through on the recording if you hear it. All right. Anyway, this is a change of variables. Is that the fire alarm? Okay. Somebody's got something very squeaky. All right. If it happens a third time, then I guess I go get to yell at somebody. Anyway, sorry about the distraction there. So this is the basic idea behind our change of variables. And what we're setting up here is we want to think about this as a parameterization. All right. The idea of a change of variables or some kind of transformation is a parameterization, and we use these to describe objects in space. So if we're doing something like we did with polar coordinates, if I have some domain that is circular, okay, I can talk about points in this environment using rectangular coordinates. All right. We can travel some distance in the x direction and then some distance in the y direction and get to these locations. All right. But it might be more sensible and easier to do this using polar coordinates. because I can more easily traverse the space. Okay? Or it gives me some way to think about how this goes together. Okay? Another example would be an arc length parameterization. If I have some curve, we can think about this curve as either being 2D or 3D. All right. One of the ways that I could think about moving along this curve would be how I move along this curve with respect to the x coordinate, right? And we're moving this way in the x direction, and my value up here changes based on what the curve is doing, right? But another way that I can think about moving along this is by following along the curve itself. Okay, that would be another coordinate system that I could choose in order to look at what is going on here. All right, and that might make the calculus easier to do if we're in that environment. Okay, we've talked very recently about spheres and cylinders, and we also have an idea where maybe we want to think about what we're doing on some kind of surface. Now, down here, this just looks like a rectangle in the x and y domain. All right, but maybe up here, I'm thinking about traveling along the way that the surface is curved. And I want to use different variables in order to accomplish that. So in this example here, maybe my x value I think about as depending upon a different set of parameters. Make sense? Okay. This is just like what we do when we switch to polar coordinates. Okay. Now, we're not used to thinking about our polar coordinate situations as a surface like this because we stopped drawing the pictures in the surface context and instead just we're looking at the integration domains. But when we're talking about polar coordinates, that's what we're doing, okay? I have some circular domain down here that's in the xy plane, and my function is some surface that lives above the integration domain. So we use this parameterization here to describe this bottom part so that I can integrate what's happening on the surface up here. Does this all make sense? Now, I just wanted to point out that we have gotten to the point to where we're skipping drawing all the pictures all the time, mostly because we can't, all right? And the other issue is that it does take quite a bit of time, okay? Now, if there's a picture that doesn't make sense or something that I need to spend a little bit more time on explaining that I haven't, please let me know. It's part of the reason why you're all here is to interrupt me, to ask for clarification, all right? But again, I feel like it's very important to reinforce this, all right? we aren't always looking at the entire picture because we are at a stage now where the overwhelming majority of the time, the figures that we make when we're talking about mathematics are graphs. Okay? Now, a graph is a picture where we have some independent variable and some dependent variable, and we plot the dependent variable in terms of the independent variable, and we have this nice picture here, right? Okay, that's what both of these things are. These are both graphs. All right. Here, y is the dependent variable. Here, z is the dependent variable. Yeah. But in our examples from the last two sections, where we've had three-dimensional integration domains, I can't draw the graph anymore because I don't have 4 dimensions to be able to sketch my picture. Okay. So don't forget about that. It's not something that we actively keep track of all the time, but it is a little bit of an issue. Okay. All right. Okay. So let's take this example here. We're going to have a square. All right. So u and v are both on the closed unit intervals. And we want to know what happens to the square under this transformation. So this is the square S. This is in the UV domain. Okay. We need to figure out what we're doing here. Okay. So if we label these sides so that we can figure out what's going on, all right. If I look at this transformation, is this transformation continuous? Yes, no, maybe. It's a polynomial. It's a continuous, right? Okay, so it's not a trick question. When we're talking about transformations, we want them to be continuous. Otherwise, they're difficult. Okay? So continuous transformation. So it should take continuous pieces to continuous pieces, right? So what it's going to do is it's going to deform this line. Okay? Yes. So the natural way to deal with this is to examine what happens to the boundary. Okay, that's what we're looking at. We're looking at the boundary of the shape, and um, if the boundary will get mapped to the boundary, and then the interior will remain the interior. Okay, so what should happen is we imagine somehow that this shape is going to get deformed into some other shape over here. Okay, we want to examine what's happening to this. All right, so the first thing that we're going to see is that if we look at, say, this point here, which is 1, 1, and I plug that value into this transformation, what am I going to get for x, y? It'll be 0, 2, right? I'm going to change my scaling a little bit in the second picture just because I drew the other one too big, and I don't want to redraw it. So that's a 2 up there. Okay. What about this point here? 0, 1. It's going to be negative 1, 0, right? Is u is 0, and I get 1 minus 1 squared, or 0 minus 1 squared for x, and then 2 times 0 times 1. Okay, so we've done those 2 points now. All right, now we need to figure out what's going on in between. Now, somehow those 2 points are going to get connected, right? And the way that that's going to happen is by us combining these two equations and doing a little bit of work. When we have S1 here, we know that V is equal to 1. Right? Okay, so this is going to allow us to rearrange things. Yeah. Okay, so we're going to do one part of this and then go from there. So we have x equals this, y equals this. We can rearrange these expressions if we want to put everything together. I want to get x in terms of y. So, I want to get x in terms of y. I divide by 2, and that gives me a formula for u that I can substitute into this. So I'm going to get y squared over 4 minus 1. And that is a downward opening parabola that does this. On this segment here. Okay. You continue this process for the other 3 sides. You'll get the boundary to map over. We can follow the orientation here of the sides. We have a tendency to map this in a counterclockwise fashion. Okay. For this one, we're going this way. Okay. Then we choose the point 0, 0 here to see what it is we're doing. 0, 0 maps to 0, 0. when u is equal to 0, we're going to end up with this segment here. Okay. We continue on looking at 1, 0. This is going to give us this point over here. The math ends up being very similar for this part as well. It looks like this. And then on the last segment, we're going to get another parabola. And I didn't draw it very well, but this is a cusp. The parabolas meet at a point. They don't. It's not the same parabola. The equation over here is x equals 1 minus y squared over 4. Okay. So we have this change here, all right? So this is what happens to S under this transformation. So this thing over here is called the image of S under, and we'll call this transformation T. Okay, so I have designated this transformation T, this stuff here. All right. And so whenever we do this kind of thing, we're going to get a new set of values over which we need to figure out what it is we're doing. Okay. Now, I know I wrote this in scary math words and pictures, but this is everything that we've been doing this chapter, right? We change the coordinate system, and then we find new limits of integration, all right? Because under the transformation, our integration domain has been morphed, right? Hopefully to something easier. Obviously, this way it got harder, right? But the value would be going this way. If I have something that's nasty and I can turn it into a rectangle, that's pretty good, because rectangles are easy to integrate. Okay? When we do coordinate transformations, this is what we're doing. We're going the other way. We're taking something that looks nasty, like a cylinder or a sphere, and we're turning it into a rectangular prism most of the time. Okay, or at least something that's really close to a rectangular prism. Make sense? Okay. Now, in order to do this, okay, Okay. So, sorry, I made a slight mistake here. So if we have a parameterization of a surface given to us by the component function g and h of u and v, okay, so this is the parameterization of a surface. And what this means is that we have some coordinates here. I have some surface that sits over the plane. I have some domain down here. Okay. And I also have a coordinate system on the surface itself in terms of u and v. Okay. R of uv is the vector that points from the origin to the point on the surface according to that parameterization. Okay, so u and v are with respect to the surface most of the time. Okay, it's a coordinate system. U and v are the coordinates that we're moving in. They are not necessarily x and y. Okay, the main point is that they're not necessarily x and y. So this is what's being described here. I can take the partial derivative with respect to what's going on with the parameterization of the surface to get this. Okay, these i's and j's do mean the thing that we're used to thinking about them meaning. Okay, so they kind of map things to where this is x and where this is y in the sense that we're used to thinking about it, right? Okay, and if I have some function, then I can plug r into it to get a height. So this point here technically would be u, v, and then f of r of uv. It's written sloppily, but we'll clean that up in a second. Okay, so we have this partial derivative here. All right. It shouldn't surprise anybody that we have r partial v. It's the same sort of thing. It's going to be some point on this surface. Okay. And the reason that we're writing all of this, okay, is that when we are moving according to the parameterization, we have to understand the difference between what's going on the curved part of the surface as we are moving away from the point here, and the linearization of that surface. So the thing that I want you to imagine is that we have a basketball. Okay? And you have an index card that you set on top of the basketball, right? You touch a corner of the index card to the basketball, and the corner of that index card represents the U and V directions, okay, that you're traveling in. All right. Now, you know the surface of the basketball curves away from this, right? But if you stay close to that corner of the index card where you have attached it to the basketball, the coordinates more or less match, right? But if we're doing calculus, we have to keep track of what the difference is between how that index card is behaving and how the surface of the ball is different, right? So that's what this picture is supposed to be showing us, okay? There's the coordinates of the basketball, okay? And then there's the coordinates of the plane that we are in due to the parameterization. And it is necessary for us in order to determine the difference between these things, because this has a different area than this does. Okay? And so we need to use calculus to track the difference of that area. We happen to know that we can use cross products of a parallelogram. So we can use the cross products of vectors in order to determine the area of a parallelogram, right? This is a formula that we have way back from chapter 12 at the beginning of the class. Okay? And so if we use these pieces of information here in order to determine the area of that parallelogram, we're going to have R partial U cross R partial V. Okay. We're going to use the bad notation for cross product here. Then we're going to have G partial U H partial U 0 because there's no K component. G partial V H partial V 0 because there's no U component here. And then we write all this out. I am going to expand on this column because it's the easiest one, using determinants by minors, right? And so what we end up with is this determinant times K. And then we have that expression here. Okay. This is what we are going to call Jacobian. All right. The Jacobian represents it's the scaling difference between the coordinate systems. So when we make a coordinate change, we're deforming our domains. I'll scroll back down in a second. but we are deforming our domains in a process like this. Okay? The reason that we used this particular square is a square of area 1, right? And if I switched to this coordinate system and I wanted to integrate using this coordinate system, I have to know what the difference in area is between this basic shape and this basic shape, because that gets added to my integrand when I do my calculations. Okay? And so it turns out that it happens whenever we change coordinates and will be a component of any coordinate switch we make. Okay? Sorry, I forgot what third letter they use. Yeah, they use, okay. They just use W. All right. So when we're talking about something like, well, let's do the example of a triple integral. If we're integrating over a region and we start off in XYZ coordinates and we're integrating with respect to some volume, then we, after the coordinate change, we'll move over here. We're now in S, where S is the image of R under the transformation, right? Because we have to morph our integration domain. Now X, Y, and Z are in terms of the new coordinates. We end up with the Jacobian being multiplied times our integrand. And then we have some choice of the three variables here. So I'm going to write dv, but really it would be some iterated integral in the new variables. All right. Making sense? My hope is that I previewed enough of the calculation part of this. We talked about polar and cylindrical and spherical, that now seeing the theory is better than writing all of this down and then now computing the Jacobians for all the coordinate transformations that we've done in the past, which is how the book does it. I think that's backwards. Hey, I think it's better to see it as we progress and then to go back and review. Okay. Anyway, so if I give you a coordinate transformation, you should be able to derive the Jacobian for that coordinate transformation. All right. It's just a matter of taking a few partial derivatives and then computing the determinant of a matrix. Okay. The hardest one that I would ask you to do is compute the Jacobian for spherical coordinates, because there's a lot of writing and a lot of trig formulas to use in order to get that to simplify, right? But we also did it in class, so you should know what to do. Okay. But I should be able to give you a short one and have it not be so bad, right? Okay. So let's talk a little bit about what the exam on Friday is going to look like. And we'll spend more time, of course, on Wednesday going through what's going on with all that. Okay. That's capital. All right. So we're talking about double integrals. We're integrating in 2 dimensions. Okay. There are 3 main ideas here. All right. Well, I guess that's the second idea. Of course, overall, we're talking about iterated integrals. Okay, if I give you an iterated integral to compute, you should be able to compute the value there. Straightforward calculation questions. All right. Okay. The next skill here is being able to either set up a problem or change the order of integration. Huh? That could be any sort of thing. Like, I could give you this and then ask you to change the order of integration. Or better yet, I could give you a problem like this and then ask you to change the order of integration. Or whatever, right? Now, obviously, this also suggests maybe polar coordinates. Okay, as kind of the main ideas here. There may be cases where you have a radially symmetric domain that, if I were really tricky, I could come up with an example where it'd actually be easier to integrate in rectangular coordinates and polar coordinates. But that would be a really asinine thing for me to put on a test. So in general, if the domain satisfies the conditions that you would expect, then you should switch to polar coordinates. All right. What you're asking about gets us kind of into trick question territory. So if you see something that's radially symmetric, 2D domain, probably a good idea to switch to polar. So both of these ideas virtually guaranteed to show up on the test. Okay, polar coordinates is very important. It's important that you recognize when it's a good idea to use it. Okay. Also remember that we could talk about polar coordinates in a situation to where the domain is an annulus or a part of an annulus. That's another situation where you might want to break out polar coordinates. Okay. And then there are also some application stuff. I'm probably not going to ask you to remember a lot of material about the applications, but I reserve the right to ask those questions. All right. Um, to use those as the context for the other parts of the problem. Okay. So make sure that you're familiar with the vocabulary mainly, and then when you're preparing your note sheets, like if there's formulas for things like moments, make sure you have access to those. But I'm not gonna try to trick anybody by just saying I'm not going to trick anybody by trying to just use like just vocabulary and expect you to remember a bunch of stuff. That's not what this is about. This test is going to be much more computational because we've been talking about integration for 3 weeks. This is an integration exam. All right. All right. 4 triple integrals. Okay. The problems on this exam are going to be a little bit longer just due to their nature. Okay. So, one of the things that I might do here is ask you a question where I ask you to change the order of integration and not ask you to solve the problem. Okay? So that I have time to ask other things. All right? Because if I ask you to change the order of integration and then solve it, that does 2 things which are bad for the test. Number 1, it makes it to where I can only ask a limited number of questions. Number 2, it means that you lose a lot of points if you don't change the order of integration correctly. Okay? So, a little bit of a this is an important skill, but I might just ask you to change the order of integration and then not work out the problem. Okay, we had a quiz question that was like this. Okay. I'm going to ask about cylindrical and spherical coordinates. Probably one and not both, just due to time. But I do expect you to be able to work out the integrals that come up with these. And to remind you that part of the transformations for these formulas involves trigonometry. Okay, especially spherical coordinates. All right, there are going to be trig functions in the integrals. You have to know how to deal with them. All right, I don't want to see tears if it turns out that you have to integrate cosine squared theta. Okay, it's not hard. We should know this, or at least remember as we're preparing for the exam. All right, so my goal is not to trick people. All right, but do be prepared for some trigonometric integrals. Okay, like sine squared, cosine squared shouldn't throw anybody for a loop. Okay, so be prepared for that, and then change of variables. Okay, you should be able to determine the Jacobian of a coordinate transformation that I give you. Okay, or derive one of the ones that we have used for our canonical coordinate changes. All right, polar, cylindrical, spherical. Um, those are questions that I could ask, and they're really good questions because you should know whether or not you got the right answer. Okay. RD theta, we know that one. RD theta dz. Well, I changed the order, but that's fine. Okay. And then rho squared sine phi for polar, or for cylindrical, spherical, pardon me. Blech. Too many round things, mixing my words up. Anywho, for here, 50-minute exam, all right. Depending on which problems exactly I choose, I'm going to see if it makes sense for me to put some true-false questions on there as well, all right. If I can fit true-false and have 4 pages of calculations, then we'll have a 5-page exam. If that doesn't make sense, then we'll probably have a 4-page exam, and I will ask slightly longer integration type questions where there's just not more difficult, just gives me a little bit more time to have you do calculation type stuff. All right. But we'll have theory questions built into what's going on with change of variables and making sure that we're doing things like setting up our integration properly, changing orders, and all that stuff. All right. Yes. I will definitely answer that question on Wednesday. All right. So enjoy your day, everybody, and I will see you next time.